Assalamu alaikum, second year students. This is Dr. J. Sadiq Basha. I am going to explain about some concepts in lesson number 2 and also some solution for the problems in worksheet number 5 and 7, something like that, in the coming slides. If you have any doubt, okay, you can ask during the online class, online hours next week, starting from March 23rd, okay, as per the timetable. So very great difficulty I prepared. So if there is any mistake, if there is any comments, you can clarify during the class, online class hours. So please cooperate and try to understand the things which is being revealed over here. Okay. So this is the first slide. So the main contents in this presentations are solution of the worksheet problem 5, steady flow energy equation derivation, and steady flow energy equation for gas turbines, steam nozzles, solution of the worksheet problem 7. Worksheet number 6 we will discuss later, so we will concentrate what is being mentioned in these contents. So this worksheet number 5, I hope that everyone is having worksheet number 5 with you, because I already gave the worksheet to all of you in the class, right? So this is just the question of worksheet number 5. So I will be teaching very slowly as usual. So try to understand things. I am going to explain how to solve this worksheet number 5. Already you are very aware about the worksheet number 4 and 3 problems, and in worksheet number 5, okay, again this is a problem which comprises of 3 important processes at a time. So you can note down the datas here, the volume, the 0.1 meter cube, temperature T1 300 Kelvin and 1 bar, pressure 1 bar, and P2 pressure is also given. Then it is then cooled at constant volume and further expanded isothermally so as to reach the condition from where it is started. So please note down the process in order. It is then cooled. Okay, the first process in the first sentence you can see 0.1 meter cube of ignited gas. So working substance is a gas at 300 Kelvin and 1 bar is compressed adiabatically. So it is an adiabatic process, first process. That is adiabatic compression. So volume get reduced and pressure increased to 8 bar. It is then cooled at constant volume and further expanded isothermally. So what is the second process? A constant volume process followed by isothermal process. Isothermal process, you know, constant temperature process. So as to reach the condition from where it is being started, means the cycle is closed. Correct? From where it started means it is closed from where it is being started. So first process adiabatic compression process, second process constant volume process, and third one is isothermal process, otherwise called as constant temperature process. So what we have to determine here, we have to find the pressure at the end of the constant volume cooling. We will see what is the pressure and change in internal energy during the constant volume process. During the constant volume process, what is the change in internal energy? The net work done and heat transferred during the cycle. So net work done, as I told you in the previous classes, so you can find any one, net work done or net heat transfer. So both will give the same answer. Okay, so better you can go for finding net work done for the whole cycle, that is equivalent to net heat transfer in the cycle, right? So again some data are given. Cp value is given 14.3 kilojoules per kilogram Kelvin and Cv 10.2 kilojoules per kilogram Kelvin. Fine, these are the data. So in next slide we will see the solution. So assalamu alaikum, just a continuation of this one. So in the given data, so you can see here, okay, V1, V2 we have to find, okay, V1, T1, pressure 1, Cp is given, Cv also given, P2 is 8 bar is there. So T1 is equal to T3. Why? Because we know that in isothermal process between 1 and 3 temperature remains constant, so T1 is equal to T3. So in the PV diagram you can see V1 to 1 to 2 adiabatic compression process, 2 to 3 constant volume process, 3 to 1 isothermal process. So 1 to 2 adiabatic compression process, the volume reduced, pressure increased, right? P1 pressure is less, P2 pressure is greater, correct? So general form of adiabatic process is P per gamma is equal to constant, and 2 to 3 its volume remains constant, and 3 to 1 is isothermal process. So this is the PV diagram, draw it carefully. V2 is equal to V3, right? Constant volume process, and those things is being mentioned over here. And 1 to 2 adiabatic compression, 2 to 3 constant volume again, 3 to 1 isothermal process. Step 4, you can find gamma, because you know Cp and Cv is given. So Cp with Cv you can find the value of gamma, and even if you put 10 power 3, 10 power 3 will get cancelled. It's no problem, so will get cancelled. So we'll get 1.402 as a gamma value. And gas constant, we know the formula Cp minus Cv, right? So we know Cp value, Cv value, so we'll get this 4.1 kilojoules for an answer, okay, for R. So how to find the pressure P3? Okay, that is the first question. Second, internal energy and net work done. So pressure P3 during the constant volume process. So P3, this is here P3 at the end of the constant volume. So this is the end of the constant volume is P3. So we have to find P3. We will see in next slide. Okay. Then change in internal energy. Internal energy during the constant volume process. This is constant volume process. So what is the formula of internal energy? MCV delta T. So MCV is the delta T. Delta T is in the constant volume process. So final temperature T3 and minus T2. Okay. So we have to find next slide. We will see next slide. Net work done is the final work done. Okay. So final work done, the adiabatic process, this one, plus work done during the constant volume process, this one, and work done during the isothermal process, this one. So in adiabatic process, what is the formula? P1 V1 minus P2 V2 by gamma minus 1. So this is 1 and 2, so no problem here. So P1 V1 minus P2 V2 by gamma minus 1. So in other words, I can write either you can use this formula or this formula. It is up to you. Okay. So that is the thing. In both the cases, V2 we don't know. V2 you can find, correct? You know that formulas, 3 formulas. From that one V2 you can find, and similarly T2 also you can find. And no, P2 by P1 is equal to V2, some formula is there, right? We already discussed in the class. So you can find like that. The work done 2 to 3 is by default it is 0. In constant volume process, the work done is 0. And for isothermal process, we have tried the formula between 1 and 3, right? So P3 V3 log E is otherwise called as ln. Okay, V1 by V3. Okay. So in here initial state is 3 and our final state is 1. And during the isothermal process, the initial state is 3, the final state is 1. So I can write either this formula or this formula, both are same, you will get same answer. Okay. If you write like this, so we are in need of here V3 is equal to V2, right? So you can get V2 formula, V2 answer from that 3 equations. So P3 you have to find, that you will see in next slide. V1 it is given, V3 also, V3 is equal to V2. Okay, so you can either use this formula or this formula. So P3 V3 is equal to P1 V1. Why? Because you know that one, right? Because in isothermal process, okay, PV is equal to constant, right? PV is equal to constant. So I can write this one same thing like this. P3 V3 is equal to P1 V1. So I can write either P3 V3 or P1 V1 here. Okay, then ln this formula, correct? We already discussed where we get, there are 4 formulas for isothermal process. Either you can use this formula or this formula, you will get the same answer. Go to the next slide. Okay. So it is a steady flow energy equation. Steady flow energy equation. So I think by seeing this name itself, you can easily understand. Okay, steady flow energy equation. So it's almost like it is the equation of Bernoulli's equation, what we discussed the last semester in fluid mechanics. Bernoulli's energy equation. Okay, almost same equation. The only thing is that we will be adding two important parameters here. One is that heat in the left hand side, heat energy, and work done in the right hand side. Okay, we will see how to derive. We are actually here, the thing is that we have to derive the steady flow energy equation, okay, for any engineering equipment. So what do you mean by steady flow? First of all, it means steady flow means the flow is the type of fluid flow which does not change with respect to time. Flow remains constant. So this is a type of fluid flow is called steady flow. This type of fluid flow does not change or does not vary with respect to time. So there is no variation when the fluid is flowing from one point to another point. There will be no change with respect to time. So what are the main assumptions before you derive the steady flow energy equations? Means mass flow remains constant. The mass remains constant. Mass remains constant from inlet to outlet. The fluid flow is uniform and compact. Means the fluid flow does not change its state. The fluid flow is only one phase. Okay, the inlet is liquid means outlet is also liquid. The inlet is gas means outlet is also gas. So the fluid flow is uniform in composition. This is the meaning. Okay, and third assumption is sum of the potential and kinetic energies during the flow from inlet to outlet remains constant. Potential energy is P and Ke, right? Potential energy, what is the formula? mg h, mass, gravity and height. Kinetic energy of mv square, mass, velocity square. So from the point 1 to point 2 it remains constant. There is no change in potential energy and kinetic energy from inlet to outlet. So there is assumption during the derivation of the steady flow energy equation. So it is called SFEE. The fluid state at any point during the flow remains constant with respect to time. That is the thing. The fluid state, okay, the state of the fluid, when you see with respect to time, it does not change. So it remains constant. So from this diagram, okay, this is this inlet. This is your inlet. This is your inlet. This is inlet, and this is your inlet. And this is your outlet. So what happens if any fluid is is being pass in the first section? So it will be having of course it will be having pressure, okay, pressure of the fluid and the volume of the fluid, and it enters in the area here, in this area A1, and it falls here in this pressure of the fluid and enters into the outlet. So the height from the reference, this is reference, right? This is a reference line or datum plan, both are same. So from the reference to here is say Z1. Similarly here from reference to here is Z2. So main thing here is the pressure P1, volume V1, okay, which enters in the area A1, and outlet it goes with pressure P2 and the area A2 here, okay. And of course we already discussed, okay, what is boundary system surroundings, right? So in system some thermodynamic process may occur. So there is a system that is being indicated over here. Boundary is the limit of the system. Okay, so boundaries, this is boundaries, these are the boundaries. Now outside, this is everything outside the boundaries, your surroundings. So in this diagram, so some fluid is traveling inside. So as usual here the fluid inlet is equal to fluid outlet, correct? Whatever the fluid is entering the system, okay, will be leaving the outlet. So the basic is fluid inlet is equal to fluid outlet. So when the fluid is traveling in the inlet, so what are the thermodynamic parameters will affect? Okay, of course there will be internal energy, because assuming the fluid has some temperature, and whenever the fluid having some temperature, 100% there will be a change in internal energy, right? So at the inlet there will be some internal energy of the fluid, there will be kinetic energy plus potential energy and flow work. Flow work means the force into displacement. Work is what do you mean by work? Work is equivalent to force into displacement. So F into D, correct? So that is the flow work plus heat energy. Heat energy is your Q. What is how much amount of heat is being present in the fluid? So it is in the fluid inlet. Then it undergoes some thermodynamic process in the system. Then again in the outlet there will be some internal energy, kinetic energy, potential energy, flow work, right, plus work terms. Because this heat energy, it has made the system to work, so it has produced some amount of work. So this is the basic equation, basic parameters in steady flow energy equation. So there will be internal energy, kinetic energy, potential energy, flow work, heat energy at the inlet. Similarly, internal energy, kinetic energy, potential energy, flow work, water in the outlet. So how to write in symbols? So steady flow energy equation can be expressed as follows. So internal energy, okay, at the inlet, so U1 plus kinetic energy is half mv square. So I am not writing v here, because v will confuse with volume. So velocity I am indicating here as c1 square. Mass I am considering as 1. Okay, so half mv square, correct? Kinetic energy is half mv square, right? So half is 1 by 2 is here. Mass considered as 1 kilogram. Okay, so velocity v1 square I wrote as c1 square. Okay, so velocity I wrote the letter as c. So c1 square. Similarly, potential energy is mgh. Mass is again I consider as 1, and height is I consider as z1, and g acceleration due to gravity, so g. Okay, flow work, I think you know that one. So flow work can be written as pressure into volume. Okay, pressure into volume of the fluid plus q. Okay, so internal energy U1, kinetic energy c1 square by 2, potential energy z1g. Okay, z1g in the inlet, g m is here, both m is considered as 1 kilogram. Flow work is pressure into volume, heat energy q. Similarly in the right hand side, same thing, u1 here, u2, where c1 means c2 square by 2, and z1g means here z2g, plus here p1 v1, here p2 v2, plus here q. So after the thermodynamic process, when the system has done some work, so it will get us work done as the output. Next step, I have brought this P1 V1 with U1 V1. That's first for simplicity. So I brought this P1 V1 with U1. So I wrote U1 P1 U1 plus P1 V1 plus C1 square by 2 plus Z1G plus Q. Similarly, same thing here. I brought U2 with P2 V2 plus C2 square by 2 plus Z2G plus W. Now, when you see this next step, when you see U plus means is nothing but enthalpy, correct? We already discussed. What is enthalpy? Enthalpy is H is equal to U plus P, general formula. So here I can write for initial state U1 P1 V1 as H1. Same thing I wrote here. Then this one for H2. So plus T2 square by 2 plus Z2G plus W. Okay. So this is the one formula when there is difference in height. In some cases, in engineering applications, okay, the height will not be, the height will be same. Say if Z1 is equivalent to Z2, okay, sometimes if Z1 is equivalent to Z2, okay, if Z1 is equal to Z2, in some cases Z1 is equal to Z2, means this quantity, this is Z1G and Z2G will be get cancelled, right? So this equation will be reduced to like this: H1 plus C1 square by 2 plus Q is equivalent to H2. Okay, this one will come, this one will come, then this will come, and right hand side H2 C2 square and work done. This will cancel when in some problems Z1 and Z2 are same and the heights are same. So this is the final equation of steady flow energy equation. Okay, so H1 C plus Cn square by 2 plus Q is equal to H2 plus C2 square by 2 plus work done. Whereas Q is heat supplied, correct, per kg of fluid. Work, W is work done of the fluid. C is velocity of the fluid, okay, meter by second. Okay, Z is height in meter. Then pressure in Pascal or Newton by meter square. Okay, and internal energy, okay, of the fluid, it is joules by kilogram. So this is the derivation of steady flow energy equation. The main equation is H1 plus C1 square by 2 plus Q is equivalent to H2 plus C2 square by 2 plus work done. When the heights are same. When the heights are not same, then we have to use this previous equation. Okay, this is the thing. So now we came to know what is steady flow energy equation. First of all, we came to know what is steady flow. Steady flow is the flow where the fluid flow does not change with respect to time. Okay, then we derived the equation step by step, and we came to know these are the final equations. In next slide, we will see how to apply the steady flow energy equation, or how to get an equation, steady flow energy equation for a gas. So in this slide, steady flow energy equation for a gas turbine. So I drew the diagram over here for gas turbine power plant. Then we will derive the steady flow energy equation for a gas turbine. So you know the gas turbine, correct? So some gas will be passing into the turbine, and in gas turbine, okay, it will be expanded. The gases will be expanded, and it will be, the gas goes out. So gas in, gas out. So what will happen here? The turbine gas, the heat will be rejected outside. Okay, and after expansion, the gases go outside, right? So this turbine does some work on the shaft, and the generator will be, start to work to produce power. Okay, to produce current. Fine. So what happens in gas turbine? The heat is rejected and work is done, right? So now how to write a steady flow energy equation in this case? So this is the question here. So let's see here how we wrote. So this is a general formula. Okay, H1 plus C1 square by 2 plus Z1G plus Q. Okay, what we discussed in the previous slide. Okay, now Z1 and Z2 we are considering as different height, but in gas turbine power plant, this height will be same. Okay, this Q here, this height. Okay, this height and this height will be same. So Z1 here, Z2 will be same. So that is the case, this will get cancelled. So we will get H1 C1 square by 2 plus Q, and H2 C2 square by 2 plus W. But the Q here, okay, the heat is rejected here, right? Heat is rejected. So heat rejection from the system to the surrounding is minus. So the Q is being replaced by minus Q here, correct? So H1 plus C1 square by 2 minus Q is equivalent to H2 will be there, enthalpy will be there, yes, C2 square by 2, yes, it will be there, plus work done by the system is doing the work, correct. Work done by the system is always positive, so it is plus. So this is the thing. So here this is the equation for the gas turbine, steady flow energy equation for the gas turbine. H1 plus C1 square by 2 minus Q is equivalent to H2 plus C2 square by 2 plus W. So this is the thing. So sign Q indicates minus because heat is rejected from the system. W is positive because work done by the system. Okay, we'll go to next slide for steam nozzles. So in steam nozzle, first of all you should know what do you mean by a nozzle. Nozzle is a device which is used to increase the velocity of the fluid. Velocity, the inlet the velocity will be less, but in outlet the velocity will be very high. So the velocity, the high in the exit section of the particular equipment. Okay, so nozzle is a device which is used to increase the velocity of fluid flow, which is widely used in thermal applications. You see in a steam power plant, before the steam turbine there will be nozzles increase the velocity. Okay, so this is a typical sketch of a nozzle, the steam inlet. So nozzle, okay, this is a nozzle, okay, and it's completely adiabatic in nature, so heat will not flow from nozzle to the surrounding. Okay, it's adiabatic steam nozzle. So Q is 0. In adiabatic process, always the the heat transfer from the system to the surrounding will be 0. So how to write a steady flow energy equation for a nozzle? Okay, so this is the one we wrote here. We know this steady flow energy equation. Okay, steady flow energy equation for the nozzle. So steady flow energy equation. How to write for the nozzle? So here, as I told you, it's adiabatic process. So Q is 0. So Q is 0 here, and work done is also 0 because there is no work here. So, okay, whatever the steam is entering inside and going outside. Okay, from the profile itself, from the nozzle profile itself. Okay, there is no work phenomena. So work done is 0, and there is no change in potential energy. Okay, there is no change in the potential, means there is no change in the gravity or the height. So these three things will become 0. So when you write this one, this is okay. When you write this is 0, this is 0, and this is 0, this is 0, right? So this is 0, this is 0. Adiabatic process is 0. Height, okay, there is no potential energy, difference in potential energy is 0. This is 0, and also this one 0. Now what is remaining component? H1 plus C1 square by 2 in the inlet, and right hand side H2 plus C2 square by 2. C2 should be there because there is a definition of the nozzle, right? The velocity exit will be greater than that of the inlet velocity. So how I can write this equation now? H1 plus C1 square by 2, C1 square by 2 is equivalent to H2 plus C2 square by 2. Okay, now suppose if you want to know the exit velocity of the nozzle, means, so doing small mathematics here. So C2 square by 2, bring the C1 square in the right hand side, and bring the H2 in the left hand side. So like if you do like this, then C2 square I can write in short form, bring the 2 in the right hand side. So C2 square minus C1 square is equivalent to 2 into H1 minus H2. So C2 square, I want C2, correct? Exit velocity. C2 is the exit velocity. C2 is the exit velocity. C2 is the exit velocity. You know that, right? C1 is the inlet velocity. C2 is the exit velocity. Exit velocity. Okay. So mathematically I can write C2 square is equal to C1 square, right hand side. Okay, C1 square plus 2 into H1 minus H2. So I can write C2, if it takes square root, so I can write square root of C1 square plus 2 into H1 minus H2. Okay, now here H is in joules. Okay, so this is the final formula for a nozzle to find the exit velocity. Okay, so C2 is equal to root of C1 square plus 2 into H1 minus H2. So this is steady flow energy equation for a steam nozzle. We will try to solve a problem based on this equation. So before solving the nozzle related problems, okay, we should know the following relationships. So this is the formula, okay, to solve the problems in nozzles. So H1 plus C1 square by 2 is equal to H2 plus C2 square by 2, or in other words, same thing, we can write the same formula in terms of like C2 is equal to root of C1 square plus 2 into H1 minus H2. Okay, where H1, H2 is enthalpies in the inlet and outlet. C1 is the inlet velocity, okay, of the steam nozzle. C2 is the exit velocity. And one more equation is also required, continuity equation. This equation we already discussed in the last semester in field mechanics. Again I am repeating for you. So mass flow rate, M is mass flow rate. How to write mass flow rate? This M is mass flow rate of the fluid. Mass flow rate. Mass flow rate. So it is in kilogram by second. Okay, the unit of mass flow rate is kilogram by second. Kilogram. Okay. So what is the formula? Rho A C. Rho means density of the fluid. Okay, density of the fluid. A means area of the nozzle cross section. Okay, A. C is velocity. Okay, so I can write M is rho AC. In other words, rho AC, I can write AC by V, small v also. You can ask why, because AC 1 by if rho is equal to 1 by V is equal to specific volume. What is specific volumes? Volume per unit mass. So I can write the mass flow rate equation in two forms: rho AC or AC by V, because rho is equal to 1 by V, right? Rho, it can be written as 1 by specific volume, right? So I can write AC by 1 by V, either this formula or this formula. According to the problem we have to use, okay, either rho AC or AC by V. Okay, AC, rho is equal to 1 by V, right? So I can write AC by 1 by V, okay, for mass flow rate. So this is the worksheet number 7. Okay, worksheet number 7 related to steam nozzle problem. So this is the inlet data available over here. Okay, enthalpy is given to 2800 kilojoules per kilogram, velocity 50 meter per second, area inlet is 900 centimeter square, so velocity 50. Okay, in the outlet the enthalpy is also given 2600, but we have to find exit velocity and exit area. So at the inlet to a certain nozzle, the enthalpy of fluid passing 2800 kilojoules per kilogram and the velocity is 50 meter per second, C1. Okay, this enthalpy H1, okay, is given. As the discharge is given is H2 is given. Okay, the nozzle is horizontal, yes, of course, and negligible heat loss. Yes, there is a diabatic process, so Q is 0, right? So we have to find the velocity C2 and mass flow rate. You have to find mass flow rate m dot. Okay, the area is given 9 centimeter square, so you have to convert to meter square. Okay, convert to meter square. And specific volume, see here specific volume is given 0.187 meter cube by kilogram. And exit area, we have to find exit area means A2, right? We have to find the exit area. Specific volume is also given, specific volume on the exit, so V2 is given here. Specific volume V1 is given. and here inlet area is given, this inlet area is A1. Okay, so in the next slide we will try to find, okay, what are the things we have to find here: exit area and velocity. Am I right? So again I repeat for you, we have to find exit velocity, mass flow rate we can find because we know the formula, and exit area. Okay, next slide we will see. So here, if you see here, there is a formula, this is the thing which is given here. So this is again I drew the diagram, okay, and these are the input data. Okay, H1 is given, C1 velocity is given, area is given, I converted to meter square, 910 power minus 4, and specific volume, okay, so 0.187, and enthalpy H2 is given, okay, H2 is given, and V2 is also given in the given data. These are given data, all are given data. So we have to find the velocity and exit area. So as usual, first to write the steady flow energy equation, they write the steady flow energy equation, H1 plus C1 square by 2 plus Z1G plus Q, okay. We already know Q is 0, work done 0, so this is the nozzle equation, correct? So we want to find exit velocity, okay. So using that formula, okay, using the formula, now bring the H1, keep the C2 in the right hand side, bring the H2 in the left hand side, so H2 become minus, so H1 minus H2 plus C1 square by 2, right? This is the formula, right? We already discussed for the steam nozzle. So I am keeping C2 square by 2 in the right hand side itself. I am bringing the H2 in the left hand side. So H2 will become negative. So H1 minus H2 plus C1 square by 2. Now from the given data we know the enthalpy H1, we know H2, right, into 1000. It is very important because here the enthalpy is expressed in kilo. So I have to convert to joules. So multiply into 1000. Okay. Plus this plus 50 square, so inlet velocity 50 square by 2, so we will get 201250 Newton meter. It is still in C2 square, then take the square root, okay, take the square root, then when you take square root you will get 634.4 meter by second. So this is the exit velocity answer. This is the exit velocity answer. Okay, this is the exit velocity answer, C2. Now here in mass flow rate we discussed the formula before, right? So since specific volume is given, I can write the mass flow rate formula AC by small AC by specific volume. Now in the inlet you have to write A1, you have to write C1, right? Then V1 specific volume. Now you see here A1 is given, right, in meters 910 power minus 4. C1 is given 50 meters 50, and V1 is given the problem. See, 51 is given the problem. So you can find the mass flow rate 24.06. You know area A1, you know C1, you know V1. So find that 24.06 as a mass flow rate. So we got mass flow rate is 24.06 kilogram by second. Okay, and we have to find one more thing, exit area, right? Exit area. Same thing we wrote here for inlet. Same formula for the exit. So mass flow rate A to C2, okay, by V2. So mass flow rate here A1, C1, V1 for inlet. Same thing for the outlet. So mass flow rate we got, okay, we got the answer of mass flow rate, that is 24.06. A2 we have to find, that is our objective here. C2 we got already, correct? C2 already we know 634.4. So C2 we know here, and V2 is given in the problem. V2, okay, it is given in the problem. So find the A2, I mean exit area. We cross multiply, do the mathematics using a calculator, and you will get the A2 area 0. It will be in meter square, right? It is in meter square. Then convert to centimeter square. Okay, how to convert meter square to centimeter square? Maybe I think you forget. Meter square, okay, to centimeter square. How much? 10 power 4. We multiply 10 power 4, okay, centimeter square. So multiply this one with this one, okay, then we will get 188.7 centimeter square. Till here also is okay, but if I ask in centimeter square means you have to, okay. So alhamdulillah, so we have discussed the worksheet number 5 problem and 7 problem, and this completes your lesson number 2. If you have any doubt, please ask me during the online class hours. This is a reference. See you. Assalamu alaikum.